Welcome to our NPTEL courses on advanced power electronics and control. This is our 7th lectures. Today we shall continue with the application and the analysis of the switches. So, we shall discuss about the switches in detail. So, based on this actually viewpoints. So, we can actually consider a physics point of view, that is device physics, the doping level, kind of material you are using, whether the high band gap material or the low band gap material, and from there we try to explain different features, then explain the operation of the fundamental features of the devices, then we shall take it a physics point of view. So, that is called device physics. And same way we talk about its switching characteristics, that is turn on characteristics, turn off characteristics, deals with the static and the dynamic characteristics, IB characteristics. Now, we require to understand how also to protect the device from unnecessary disturbances, surges and the hazards. Unnecessary disturbances and surges, and we require normal protections like high DVDT protection, DIDT protections, thermal runways. So, focus on the electrical and the thermal stresses within the device. Drive viewpoint, that is actually emphasis on the switching behavior of the power electronic device, which can be applied to the different kind of driver circuits. Modeling viewpoint, we have a different kind of model. We have a SPICE model of the power electronics. So, it is a state space model. So, we can write we can have a different kind of modeling viewpoint, what kind of simulation tool should be used. Based on that we have a different kind of approaches. So, simulations and the hardware implementation or hardware in a loop applications kind of thing. We have a many kind of hardware interfaces like RTTS, OPLRT. So, there we try to find it out the solutions of a few systems, and we try to model the power electronic switches. So, we will be modeling more realistically. So, that is actually the modeling viewpoint. And packaging, so it comes under different kind of packaging. So, because we want that the devices to be compact, it maybe comes across in a ceramics packaging, it may comes across the plastic packaging depending on the thermal runaway and different kind of cooling systems and the compactness. And so, it comes at the device mounting strategies, removal of the heat sinks and how you will dissipate the heat in different way, and force cooling devices and the connection issues. These are different criteria to choose a particular device, because please understand that modeling of the viewpoint is also important, because once before put in the hardware we generally simulate a system. So, if it is not very authentically simulated, then actually the fidelity of this model is in a questions. So, all those aspects has to be considered while actually taking a consideration of a switch. And when you are considering a switch, we always assume, this is the ideal conditions, that no resistance or 0 forward voltage drop. Offset resistance is infinity, when it switch is off no current flows. When on conduct, it can carry infinite amount of the current both in forward and the reverse direction. It comes under some kind of mechanical switches like SPST and all those things. When off, instantaneous infinite forward and the reverse voltage. So, you have studied the forward breakdown voltage, reverse breakdown voltage, but in ideal consideration of the switches, this has not been considered. It can switch instantaneously, that is also not the case, because it has a finite turn on time. We have referred to the data sheet of the different device and we have seen that different turn on and turn off time. Instantaneous off and on time and from on off states. So, transition between on and steps is basically does not take any time, it is basically an instantaneous phenomenon. Power dissipation of the switches is 0. Why? because when voltage is high, when it is blocking the voltage, no current flows, and when it is conducts current, there is no voltage drop across it. So, both conduction and the switch transition losses are also 0. On to off or off to on transitions of the switches are fully controllable. So, we can wish to turn on and turn off wherever it is required, but we will come into such picture that even if actually in a different kind of topologies in future, even if we have triggered current due to the direction of the current, switch will not take the conduction till current through that other device goes 0, then only transitions comes into the picture. But in ideal condition, we assume that whenever I wish I can turn it on, whenever I wish I can turn it off, and it requires no power or to drive or control the switch. So, power losses in a driver circuit is 0. These are the ideal characteristics of the switch, and ultimately you will see that all switch deviates from it, and so we have to find a closer approximation to these ideal conditions while we are analyzing and discussing about the switches. So, for this reason we have few ratings and specifications. So, this is what we are saying, that its forward blocking and the reverse blocking capability is infinity ideally, but actually you have a voltage rating that will specify your forward and the reverse voltage blocking capability. The switch should have ideally infinite current carrying capability, but datasheet will prescribe the current rating of the device. Transition from the switching on to switching off and vice versa is infinitely small or it is instantaneous, that is the ideal characteristics, but switching speed and the frequency will have a limitation on it. Same way DIDT protection, so that is also comes into the picture in transitions. So, high DIDT leads to the damages of the switches, so we require to protect from it. Same way high DBDT also leads to the damage of the switches, we require to give a protections. What we assume that what we ideal characteristics, there is no switching losses, but there will be a switching losses. So, we require to calculate it, accordingly we have to choose the switch. Gate drive, we have said that gate drive does not require any power, actually it requires power, and gate driver requirements are many things, what should be the amount of the current sink into the system and what are the pulses it can generate, these are the issues. Safe operating zone of the devices, which voltage and which current it can operate safely, so that it does not go for the thermal runaway, and I square rating for the fuse and other devices. Temperature, different junction point have a different temperature, we should ensure that it does not crosses the thermal limits, and also the thermal resistance from the heat sink to the body. So, what are the actual path of heat dissipations. So, these will be specified, we have seen already in the data sheet, this data has been specified. So, mainly switch depend on switching rating, that is which they handle power and the product of their current and the voltage instead of their power dissipation rate. So, higher the power dissipation rate, we say that switch rating will be higher, and we shall find that thyristors is actually the first person in that category, first entity in that category. Consequently, the major attractive feature in the power electronic is its capability to dissipate low power or the no power. So, there are different kind of loss. When it is on, even though we assume that the power losses across the switch is 0, but is not 0. So, thus we have a conduction loss, and thereafter when it is turned on and turn off takes place. So, there is a switching loss and also there is a loss at the gate driver. So, these three losses we have to actually accommodate. Switching loss comes with the turn on and turn off losses, and conduction losses is depends on, sometime it is RD on, into I square for the MOSFET, and other device is a constant voltage drop into the current. So, from this discussion we can come out to the switching device choices. One is semiconductor device. So, it can be uncontrolled and controlled. So, under uncontrolled it comes to the rectifiers and the accessories. Thereafter it comes to the power silicon diodes, Schottky diodes, fast recovery diodes, and there is accessories like this is used mostly in the protections and the regulations. These are DAC, Zener, MOV. Thereafter within a controlled we can classify it broadly in the three categories. One is regenerative. So, you want that power to be feedback from the load to the source, like for example, when you are using electric vehicle and you are braking or you are going to the downslope, then power should feed it back to the source for the better utilization of the power. And if you wish that regenerative braking from, we will use the device like SCS, track, GTO, and if you are using, because it is a current controlled device, so as long as current is high it can be a bidirectional. And you can have a non-regenerative, that is BJT, IGBT and MOSFET. Generally MOSFET comes with the body diode and thus also have a regenerative braking capability, and to make IGBT and BJT regenerative we require anti-parallel diode parallel to it. So, and thereafter it can have a integrated packages, that is IGCT. So, it packages actually the MOSFETs and the IGBT together. Thereafter intelligent power module, power PIC, this kind of entities are also there. So, you see that actually power conversions capacity and the switching frequency. So, different kind of power handling capability is being used. So, for low frequency applications you can have a thyristors and where power handling capability as high as 100 of megawatt. So, it finds its applications in HVDC. Thereafter you got an GTO. So, where it is a little high frequency and quite high voltage or high power. So, for this there is a high power drives and railways. Thereafter whole zone comes under IGBT. So, IGBT is basically feeding, you can see the actually very big portion of the power electronics. So, it can handle power to some level up by paralleling hundreds of kilowatt. Thereafter for this is an application is a UPS, distributed power supply, small motors inverter, small drive or medium voltage range drive, electric vehicle applications. Thereafter it comes, thereafter you go to the higher frequency and little less power, then it comes to the MOSFET. The bipolar transistor has seen a lowest duration nowadays due to the advent of the IGBT. So, that generally is bipolar transistor is have phased out most of the cases. MOSFET will have a very high frequency, but low power handling capability, and that finds its application is switching regulator, SMPS, VTR modules of the phones and power ICs and all those things. So, these are the power ratings and the frequency ranges that is available for the existing device, and what kind of device we will choose based on those criteria has been discussed here. And new entrant is basically the this is a SI limit, the SiC, and SiC is a material instead of the silicon, and SiC will have an advantage of they are pushing the power of 10 to the power 3. So, if it is a power MOSFET of SiC, so that can come into the IGBT range. So, if it is actually an IGBT can come to the GTO range, and GTO can come to the easily the thyristor range. So, this is the advantage of the SiC devices. So, we have discussed about actually power diodes, and the power diode we have classified that is based on its recovery time. So, this is called pin diode, and it is used in fast and ultra fast rectifiers. Mostly it is a DC to DC applications, isolated DC to DC or non isolated DC to DC applications, and the PV systems. And thereafter we have a Schottky diode. This is used for the power rectifier, mostly in case of the active rectifier where you are making AC to DC, keeping THD limit low, and thereafter solar cell applications. So, that has a first recovery. Mostly first recovery diode is used mostly in the SMPS, where actually switching frequency required to be high, and it is mostly used in a parallel with the MOSFETs. Thyristors mostly used in high power rectifier, rectification of the high power AC in high voltage DC power transmissions. All our actually the your railways, those who are actually suburban trains, still they use actually high voltage rectifiers used to control the welding of the machine, mainly MTAW, metal tungsten arc welding, and the gas tungsten arc welding, this kind of thing. They are actually it finds its applications. It is used as a switch for different devices and power regulators and the motor control, because it is uncontrolled device. Based on this actually voltage polarity it will conduct, and sorry, it is a semi controlled device, and for this reason where actually high power requirement is there and we can make the current leading, then it is will automatically commutated, and thus in this kind of applications thyristors finds its suitability. Now comes to the GTO. It is uses in high performance drive system such as a field oriented control scheme, that is vector control for the high power motor drive, robotics, machine tools. It is used for the traction application because of the lighter weight, and it used in high power inverters where GTOs cannot feed the power. They are used in the DC drive and fax devices and DC chopper, used in AC drives for rectification operation of the high power application, used in stabilized power supplies, used in high power induction heaters, and used static var compensator or different kind of fax devices. MCT mostly it finds its application in the circuit high power circuit breaker. It uses high power application like high power conversions. They are used for the induction heating. UPS system is also used for the converter, DC to DC converter, high power DC to DC converter, mostly used for this actually harvesting power from the offshore wind plant or something. Power handling capacity can go as higher megawatt level. Variable power factor operations are used as a force commutative power switches. Now IGCT is a new entrant. One of the application of the IGCT, it can handle around 100 times or 1000 times more power than the IGBT, the same actually frequency range. Variable frequency inverters is definitely a preferred choice for it, because we can go to the high voltage applications, and if we run at a high frequency, since you have heard about the V/F control and we can track the switching frequency a little higher, then we can have a high power gearless operation. That is one of the challenge we are facing, because once we have a very high power drive, if you wish to go for the higher power rating, then torque compromises. So keeping torque same, if we wish to go the high power, high speed, so this kind of application where IGCT has been preferred. Drives and tractions, so it is a preferred choice, and multiple IGCT can be connected in parallel and series to actually increase the power handling capability of the line. Same way STIH we have discussed already, used for the system of the energy accelerators. So, inverter with the soft switching, that is actually we can make the switching losses low or 0, that is called soft switching. That can be ZVS or ZCS. That means ZVS is 0 voltage switching or ZCS or 0 current switching. That can be easily achieved by this SIT, and it is one of the member that find very good applications for the current source inverter. We will come across this voltage source and current source, different kind of topology, and we shall discuss about it with that these switches. Pulse power inverter. So, this kind of application is quite natural for this in case of the pulse, mostly in actually welding kind of application. Now, let us come to the MOSFETs. MOSFET is used for the high frequency low power drives, motor control applications. There are DC choppers, linear voltage regulators, power supply, etc. So, you can see that these are the different applications of the IGBT. I have seen that IGBT fit into this actually day to day application quite well. So, we have a modern elevator that is having adjustable speed drive, and these are run by the IGBTs. So, power goes to hundreds of the kilowatts. There you may have a inverter servo robotics. So, that we use for the different kind of mining operations mostly. There are the arc machine or arc coiling, where we want to maintain also power quality better. Power supply is UPS, SMPS for high data bank kind of applications, transportations for the railways and all those things, and battery charger, electric vehicle. These are whole area is of IGBT. Now, let us come to the protections. We have talked about DVDT and DIDT protections. Now, let us, and how you can achieve that? We achieved by Snubber. Due to the shortage of time, we shall take it out for the thyristors, and this concept can be extended to the all the switches we have talked about. The switching device and the circuits component may fail due to the following reason. So, failure may come due to the thermal failure, or that is called thermal runaway, overcurrent and over voltage. So, these can be controlled by the supply side, but and also it may cause with the excess DIDT and the DVDT. So, that may actually cause failure or reduce the lifetime of the switches, and also excessive switching loss while conduction. So, we require to reduce these two losses mainly by Snubber. Power electronics and other switching device and the component can be protected from the overcurrent by placing the switchable fuses or the MCB or now different kind of circuit breakers. Heat sinks with a different kind of cooling technique, fans are used to take out the excess heat. And what Snubber will do? Snubber circuit required to limit DIDT and DVDT and the over voltage during turn on and turn off of the switches. So, there are different kind of Snubber. So, this is the device we require to protect. To protect that device, we require so many devices. So, anyway, so this L will be in a series with the device, and this will ensure the protection over DIDT. It will limit the DIDT protection, and this RC network will come while turning on, because once actually current flows, if it is off and this is the actually voltage across VA is greater than VB. So, and you are triggering, then this will come for high DVDT protection. And also while actually taking off, this capacitor will ensure that actually current flows through it through this R1, and ultimately it gets the capacitor charged in a reverse manner, and it will ensure that relief over the DVDT. Same way we can have a different kind of circuit. Here value of R1 is more than R, and mostly it is comes into the picture, because if you see that actually this is RC network that is charging, and this is the time constant of the circuit, and will ensure the time constant of the circuit in such a way, and that time stress across the switch does not come. So, once capacitor is fully charged, whole stress will come across the switches. And if we use reverse polarity, the inductor will be in the same position, and what happened here, actually this R has to be set beside and R1 will be here. So, it comes into the picture, these circuits, while actually in turn off, and it is called a reverse polarized Snubber circuit, and it will actually protect for DVDT protections. And same way we have a unpolarized Snubber circuit. So, it can operate both the connection, it is with the, this is RCD snubber, this is RC snubber, and your time constantly required to be chosen in such a way that stress, DVDT stress across these switches get reduced. Since it is unpolarized, it can operate for the bidirectional thyristors. So, where Snubber finds its applications? So, let us consider the simple chopper kind of operation, and you have a high source inductance. Then you will have to provide the diodes as a snubber to have a, and since it is a high, and we can assume that load is a high current source. In this condition, you have to allow flow of current continuously, and thus it will find this path like that while turning off. So, this diode comes into the picture while turning off. Similarly, power MOSFETs turn off. Once the gate pulses is been withdrawn and negative gate, little negative gate pulse, so ultimately this switches does not have any voltage, so it is short. So, gradually it is actually getting a forward blocking voltage capability, and thus capacitor will be charging. So, what will happen? Since capacitors will start charging this way, so automatically actually current through this MOSFET will go low and will have a high DVDT protection. So, this is thyristor snubber what we have discussed here, and so this is the RCD snubber, and it is used for the thyristors, and this is the snubber used for the GTO, same snubber, and it can be used for the GTO. This is the turn on snubber, and this will be the turn off snubber. So, we shall continue to the requirement of the gate drive. We have talked about the protections, and in next class we shall talk from the gate driver circuit, and we shall looking forward to start about the different features of the gate drive circuit in our next class. Thank you.